I think we stopped on this page on Monday. Okay, lest I forget, the first continuous assessment will be coming up next week, Wednesday, for Physics 104 and Physics 105. So next week, Wednesday. So by Tuesday, you should have sufficient information on the notice boards at Physics department. So you are expected to arrive at your venues at 7:30 a.m. And the two tests are meant to last for, I think, 40 minutes or so. So in the last class, we spoke about applications. So the applications of electric and magnetic fields, where we spoke about the velocity selector, describing the max, the X max, the cross max on the screen as direction of magnetic field pointing into the screen and electric field pointing from the left side, the plate on the left-hand side to the plate on the right-hand side. The plate on the left-hand side is positive, that on the right is negative. So the direction of electric field is from the left to the right. And we haven't established that the velocity of the charged particle that is given this source traveling in between the electric and magnetic field will depend, also will determine the magnetic force. The magnetic force that will exert on the charged particle depends on the velocity and charge of that particle, whereas the electric force depends just on the charge of the particle. So the way it operates is that the magnetic and electric fields are fine-tuned such that only particles with a certain velocity v will go through undeflected. So those that have velocities that are greater than the desired velocity, they would experience larger magnetic force. They will tilt to the left, crash into the positive plate, and those that have lower velocities will experience smaller magnetic force, such that it will tilt to the right and crash into the negative plate. So for it to move undeflected, you must have a velocity that coincides with the magnetic field strength, so that you have a magnetic force that will be equal to the electric force. So since magnetic force is pointing to the left, electric force is pointing to the right, when both of them are equal, then the resultant force will be zero. So moving from that, we move to some other applications, which is called the Brain Bridge Mass Spectrometer. The mass spectrometer, the Brain Bridge Mass Spectrometer separates ions according to their mass to charge ratio. So, and it involves the use of a velocity selector, which is a combination of electric and magnetic fields, and also an additional field that is made of just magnetic field without electric field. So the only relationship, the magnetic field at this second region is described here as B naught in, while the one at the velocity selector is P in. So the velocity selector here starts the work by ensuring that the particles that are coming in have a definite velocity. So the particles with definite velocities enters into the second region through this opening. And when they enter, what they experience in the second region will be just magnetic field without electric field. And the magnetic field they experience in the second region will make them deflect depending on the nature of their charge, and also depending on the ratio of their mass to charge. So imagine a stream of charges entering into this region, and this line, this black base here, are detectors. So when a charged particle crashes into the charged, sorry, into the detector, the length is determined to know the radius with which the charged particle traveled. So when a charged particle enters through this opening, the path turns into a circular one. So it travels in a circular motion in the field, having a certain radius r. So when it enters here, it's possesses a certain radius r. So let's continue. So let me read again. The mass spectrometer separates ions into their mass to charge ratio by first passing the beam through a velocity selector, and then passing the beam through a second uniform magnetic field that has the same direction as the magnetic field of the velocity selector. So the first and second magnetic fields have the same direction. They may have different magnitudes, but they have the same direction. That is, the direction of the magnetic field in both cases, as you can see, is pointing into the screen. So upon entering the second magnetic field, the ions move in a semicircle of radius r before striking a detector at P. If the ions are positively charged, they deflect to the left. So assuming these charges are positive charges and they are deflecting to the left, if they were to be positive, negatively charged, they would have deflected to the right. So the direction with which they move, I think we established that in the last class, depends on the nature of the charge. So we should remember this, our formula. I think we have a formula that told us earlier that, let me go and it's mv over r equal to mv over r equal to qb something. Let me go and spy. Yes. Okay, this is what I wanted to remember. mv over qb equal to r. So as good as mv over r equal to qb. But let's take this one, mv over qb equal to r. So I will say mv over qb equal to r. We can, from this expression, we can determine m over q. So by saying what is m over q, we'll be having m over q equal to rb over v, right? So, and the b we are talking about here is the b naught. The b naught in this second region. So what that tells us is that a certain mass overcharge will, if you have a certain particle that is having mass to charge ratio m over q, it's having a mass, the particle is having a mass measured in kilograms, having a charge measured in coulomb, and it has a mass to charge ratio, the mass divided by the charge. The mass divided by the charge can be defined as the radius with which it will cover times the magnetic field strength divided by the velocity with which it's traveling. So in this case, we've established that the velocity is the same for all the streams of electrons, right? Because the electrons are coming in, having gone through a velocity selector. They are all coming in with a certain velocity v. And they are all entering the same region V naught. The only thing that can change here is the radius. So that means that some particles will be crashing here, some will be crashing here, some will be crashing at different points to the left. They'll be crashing at different points on the left, crashing in a semicircular path, giving them individual radius r. So this particular radius r would give us an idea of the mass to charge ratio. So moving forward, we must have seen that V is equal to E divided by V, that is the velocity V. Velocity V is equal to E over B. I think the one we should be used to is to say that E is equal to VB. Right? When you say the magnetic force, F is equal to QV cross B, and we say the electric force, FE, is equal to QE, and we say that for them to go through the velocity selector undeflected, FB should be equal to FE, right? That means that for you to have FB equal to FE, then we should be having something like QV cross B equal to QE, right? For you to have it travel undeflected. So for you to have a particle travel undeflected, magnetic force should be equal to electric force, and we define the electric force to be product of the charge and the electric field strength. And we've also defined the magnetic force as a cross product of charge and velocity vector with the magnetic field vector. So these are also vectors. So from this expression, it's easy for us to say we are dividing both sides by Q, right? And we'll be left with VB or V cross B equal to E, that is the cross product of velocity and the magnetic field strength will give us the electric field strength. So we should not be surprised when we now come to say that if we can say, if there is no argument about this, then we can approximately say that V is equal to E divided by B. And saying this, we can come here to replace the velocity we have here with E over B, and that gives us R B naught B. So now the second B, the velocity we are talking about here, it depends on the electric field at the velocity selector and the magnetic field at the velocity selector. V naught, which we use there, is talking about what happens in the second region. But from the expression of V, the velocity depends on the electric field and magnetic field at the velocity structure at this first region. And that is why we have B here and not V naught. So in short, with the knowledge of the magnetic field strength at the second region, the magnetic field strength at the first region, the electric field strength at the first region, the radius of deflection directly tells us the ratio of mass to charge. So by determining the ratio of mass to charge, if you know the ratio of mass to charge, when you know one of them, you can determine the other easily. That is, if you eventually determine mass, then you can say this is charge. And if you determine charge, you can say this is the mass. If you remember the Thomson's experiment, they did something like this to determine mass to charge of the electrons. So from the mass to charge ratio, we measure the radius of curvature. And this application is used to determine the masses of different isotopes. So when you have different isotopes, knowing that they have similar charges, then the difference is the mass. So at least you'll be able to know that you have different isotopes and the ratio of their masses is easily determined. So another application of electric and magnetic fields is a cyclotron. So a cyclotron helps us to accelerate charged particles. You know, when a charged particle is placed in an electric field, it experiences electric force. When force is experienced, the normal thing you should expect is acceleration. When you are experiencing a force, you should accelerate. That is when you are experiencing, let me say, a net force, because you can say, are you not experiencing force and you are still? When you are experiencing a net force, you are bound to accelerate. And if you are experiencing a force and you are not accelerating, it's most likely that the force you are experiencing is equal to the force that is resisting you. So when you are applying a force, that is, for instance, so in your car, you are pressing the throttle, you are, and notwithstanding, is still moving at a constant speed. That means that you are experiencing some frictional forces, maybe air resistance on the road, anyhow, that is countering your the petrol you're adding. So, and when we say acceleration may not necessarily mean just ordinary change in the rate at which you move. It's a change in direction. It's also acceleration. When you are moving in a curved region, you're also accelerating. For instance, when the charged particle enters the second region, it's also acceleration for it to curve. It's changing direction. So when direction is changing, it means velocity is changing. And when velocity changes, acceleration occurs. So how this operates is that at the center here, at the center P here, the charged particle is released at the center P here. But we have two disks here, disk D1 and D2. So disk D1 and D2 they have magnetic fields, so they make the charged particle to curve in a semicircular path. But in between those two disks, we have electric field that is set up. And what does the electric field do? It will accelerate the charged particle. So imagine, I don't know how large this is. So I have another slide ahead that will show us what happens there. But the major point is that it starts from the center, it begins to accelerate as it moves around the disk. And when it has accelerated so much, then what it happens eventually is that it leaves the cyclotron with a very high speed. So, and what happens here is that between these two disks, where electric field is set up, we have alternating voltage there. So let's assume this particular part is positive and this is negative, you would expect the electron to accelerate towards the positive plate. It will curve before it leaves this semicircle. This would have turned to a negative plate, and the other one would have turned to a positive plate. So it will accelerate again into the other disk before it leaves D1. So okay, this is D1, this is D2. Before it leaves D1, this D1 would have turned to negative, D2 will be positive. It will accelerate again into D2. Before it leaves D2, the polarity of the disk will change again so that it will accelerate. So it will keep accelerating as it enters D1 to D2 and D2 to D1. The acceleration will keep on going on and on and on and on until it eventually leaves with a high velocity. Okay, so when we are talking about leaving with high velocity, then we should talk about the kinetic energy, which is defined, or which has always been defined as half mv squared, where m is the mass of the charged particle and v is the velocity. Then from this, we should also remember that what's that our formula again? I think I can remember mv over r equal to qb. Then if I remember that, then I should be able to say that v is equal to qbr. Oh, this my writing is too. Okay, I said mv, come on. mv over r equals to qb. And I can say that v is equal to r qb over m. Then v squared should be r square, q square, b square over m square. So v square. Then half mv square will just be adding half mv square. Will also be multiplying this by half m. M cancel m squared. It remains m. Then what we have here is q squared, b squared, r squared over 2 times m, 2m. So the kinetic energy can be determined by the charge, magnetic field strength, radius, and mass. Okay, so this slide tries to explain what I tried talking about here, which is we have uniform magnetic field in this region, this semicircular disk, let's call it D1, and also uniform magnetic field D2. Then at the center of both disks, that's the injection point. here the charged particles that we want to accelerate is inserted. So by just inserting it in this particular place, there are some arrows that shows how they travel. Then you would expect it to turn around and begin to spin out in this direction. And why is it spinning out? Because the electric field within this region, that is the region between both magnetic field, the disks, both this D1 and D2, have alternating voltage source. And what that does is that it's a well calculated voltage source, such that as the charge particle is leaving, the charge on the plate changes. So whenever it's leaving a plate or a disk to the other, we would always have acceleration. So this is the side view of the disk, which shows that on the side we have north pole, south pole for the uniform magnetic field, and in between we have electric field to further accelerate the charge of the, so to further accelerate the charged particle. So we are familiar with this expression. I think we spoke about that some slides away. So looking at it, there is nothing new. There's T 2 pi r over V. So from that expression, we can determine omega. Omega should be 2 pi f, right? Omega, right? Omega should be 2 pi f. That's angular frequency. And f should be 1 over t, because we are the expression here, t here is period. So we can say omega is 2 pi over t. So when we say 2 pi over t is omega, then we can say from this expression, we can say that our omega, since 2 pi over t is omega, we can say omega is V over R. And we have expressions for R. We can bring in the expression for R from these are our equations, mv over R equals to QB, and we have this beautiful expression called the cyclotron frequency. So that's one of the reasons why I like physics. All you need to remember are just a few things, and you reserve your large fraction of your memory for some other things. Unlike history, where you have to memorize everything, where there is no connection, where there is no link. So let's look at another application, the galvanometer. We've spoken about galvanometer as a device that measures current, right? When we're talking about piston bridge, you said it helps to measure current flow, right? Okay. So if you have now the galvanometer can be used as an ammeter or a voltmeter. Since it measures current flow, if you want to measure larger currents, all you need to do is to connect a shunt in material of very tiny resistance across in parallel to the galvanometer, so that when current is coming, the larger chunk of the current will flow through the shunt, through the low resistance resistor, and very tiny currents will flow into the galvanometer. And knowing with the knowledge of resistors in parallel, you can determine the actual current that is flowing. Have we started again? I think we should move faster. So, with the knowledge of how resistors flow in how current flow in resistors in parallel, you can determine what current flows through the other channel when tiny current flows through the galvanometer. And when you want it to act as a voltmeter, voltmeters are connected in parallel to our circuits. If you recall from the first circuit we had when we were discussing Ohm's law, the voltmeter was connected in parallel. Let's see. Okay. So the voltmeter is connected in parallel to the resistor to determine the voltage drop across the resistor. So when you want a galvanometer to function as a voltmeter, you need to connect a high resistance resistor in series with it so that tiny currents will flow through it. So, but that's not even our business for now. Our business is how does the galvanometer, how does it work? And the way it works is that we have a coil embedded in between magnetic fields such that when current flows through that coil, there is a deflection which depends on the current that flows through that coil in the galvanometer. So that's the basic principle. The working principles of the galvanometer based on electromagnetic interactions between current and magnetic field. So over here, we have the magnetic field, North Pole, South Pole, and we have a coil in around the pointer. So when large current flows, you would expect larger deflection. You would expect larger magnetic force to be experienced when large current flows through the coil. And when large current flows through the coil, it will deflect more than when tiny current flows through it. So the current that flows through it determines the extent of deflection of this pointer. So what that tells us that when current flows, magnetic force is also experienced. Very soon we'll be saying that when current flows, magnetic field is also set up. So in this scenario, when current flows, you expect the pointer to deflect because when current flows, magnetic force is set up is set up turning the coil to the right. Since since it's a force, you should expect it to keep moving. But there is also a restoring spring to keep that in check. If not for the restoring spring, regardless of the current that flows, it should get to the end of the scale. But for the sake of the restoring spring, it will keep it in check. And the restoring spring, the force, the magnetic force that is applied needs to balance with that of the restoring spring in order for it to stay at equilibrium. So let's just read through. The figure shows galvanometer consisting of a coil of wire loops in an iron core that pivots between the pole faces of the permanent magnets. When the current is in the coil, the torque is exerted on the coil. A small spring supplies a counter torque, and when the two torques cancel, the pointer indicates a deflection angle that is proportional to the coil's current. So I think that's Straightforward. Okay, we just look at briefly Maxwell's equation all through, and in continuing after this moment, everything you are doing can be summarized by 4 Maxwell's equation. And these are the first two that talks about the divergence of electric field and the divergence of the magnetic field. So, and the first is Gauss' law, which says that the total electric flux through any closed surface equals to the net charge inside the surface divided by E naught. I think we've seen something closer to this in the course of our lecture. So if you assume you have a charged particle, enclosed in a sphere, then the total flux that will go out of that sphere, the area of the sphere should be 4 pi r squared, and the total electric field should be 1 over 4 pi epsilon naught r squared, and the charge Q. So multiplying them together will give us Q over E naught. So the total flux that's through a closed surface equals to the net charge. The enclosed surface, which is easy here, is a sphere, 4 pi r squared as area. So the product of the electric field and the area, E is electric field, A is area. So the equations have also been written in 2 different forms. We have the differential form and the integral form. So, and they both tell us the same thing. So the second one is the Gauss law of magnetism, and it tells us that the net magnetic flux through a closed surface is 0. And if you think about it as magnets don't exist as monopoles. They exist as both north and south pole. So the number going out will always be equal to that coming in, and that will add up to 0. So the net magnetic flux through a closed surface is 0. And we have the third and fourth law, which are called, we call this divergence of E, divergence of B, but this is called E, C-U-R-L, curl, like Jerry curl E and curl B. So this is the first one is in Faraday's law, and it tells us that the EMF, which is the line integral of the electric field around any closed paths, equals the rate of change of magnetic flux through any surface bounded by that path. So if you can state Faraday's law, you will not be saying anything different from what is here. And we also have the Ampere-Maxwell's law, which is the curl B, and tells us that the line integral of the magnetic field around any closed paths, there's a sum of mu naught times the net current through that path, and epsilon naught mu naught times the rate of change of electric flux through any surface bounded by that path. So these 4 equations are set of equations that have actually changed our world, talking about electromagnetism. So, but for physics 104, let's just keep it that way and let's move forward. Yes. 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 The way I will answer a question is to say that the direction of line of force for electric field. For instance, I think I have a blank page somewhere here. For electric charges, when it's positive, we say the line of force is directly radially outwards, and the arrow points outwards. And the relationship here is, the assumption here is to say that whenever you bring a positive charge around here, what direction will it go? It will go in the direction of that line. When you have a negative charge, also because it's electric charge, the lines are directed radially outwards. Well, sorry, this time directed radially inwards. If you put a positive charge again, in what direction will it go? So the electric lines, of course, are directed radially outwards or inwards, and they give an indication of where will that positive charge, where will it go if you place it in. For a magnet, we cannot separate them, North Pole, South Pole. And we have the lines of force like this. And so the arrows point from the north. Oh, my man. The arrows point from the north to the south. So at the South Pole, it points inwards. And at the North Pole, it points outwards. So what this tells us is that if I bring a North Pole, though I cannot bring it in isolation, but if I put a North Pole here, in what direction will it go? It will move in this direction. It will want to move. If you bring a magnet here, a small magnet here, which is North Pole, South Pole, this north will repel this north, this and also this south will repel this south. But the direction of, we are considering this direction and this north, it will want to move in this way. So when we talk about plotting the lines of the magnetic lines, we talk about the small compass, which responds to the magnetic field, and direction depends, it will point depends on the force it's experiencing. Okay. Okay, you can look at it like positive and negative, fine. And when a charged particle is passing, it actually knows if it is north or south. When we are talking about the direction of electric field, we usually talk in the direction of positive plates to the negative plates. When we are talking about the electric field as well, it also has direction, North Pole to South Pole. So when a charged particle is traveling through a magnetic field and it deflects to the left, if it were to be traveling in the opposite direction, it would have deflected to the opposite direction. So the charged particles, they actually know that this is north, this is south. They respect the direction of the magnetic field, just like the magnetic field also respect the charges of the charged particle. I was thinking you will talk about what things we have spoken about at before or at the end of meter bridge. Any question before getting to meter bridge or at meter bridge or at potentiometer? So like I said, my hypothesis is right. There is no need to worry. And the questions will be very simple. You don't need to prepare. Don't prepare, just come unprepared. So you'll just be seeing questions like resistor A is 5 ohms, resistor B is 3 ohms, which is greater, 5 or 3. But since you have complained, I will not do that. Since you have complained, you said, no. So for that reason, I will not do that. I will not do that. Because I don't like embarrassing students. I don't like embarrassing students. And I see now that it's already embarrassed that, with all my credits in my egg. So we can continue from here next week, Thursday. I think Friday and Monday is another time to pass to Easter.